got it, right? So on Wednesday, at the very beginning of Wednesday, I'm going to talk about the homework and go through all the problems and give you more hints so you can work on. Then it will be due Friday. Is okay? Or you want me to go through every Monday, then you have more time to work. Monday is better, or Wednesday is better for me to go over all the homework to be due. No opinion? Wednesday? If I talk about the homework problems on Wednesday, you will have 1 day to finish. What is okay, right?
Monday.
It's due,
Monday.
it's
Due
due
Friday.
Friday night.
Yeah,
So, I mean, if we have questions after Wednesday, we can just talk to you on Friday.
right. Yeah, Friday.
Yeah.
Okay, that means on Wednesday, right? You want Wednesday. Okay, so yeah, so this is several things I need to talk to you. So then we talk about this problem. Okay, so we are going to follow this pattern, and every Monday I give you 3 lecture notes for Monday, Wednesday, Friday, and then I will go through this. You just pull out the lecture notes I give you and jot down important information. If this is necessary, I'm going to write the derivations on the board. Okay, so have you guys got a chance to solve this problem? So what is the problem is? So the problem is that there's 2 steps. And first step is that what is the penny shape and this crab. And we use this equation to calculate. So this equation, sigma f, and we want to know under what condition when sigma infinity equals what? We call it sigma f. When the infinity equals sigma f, and so we want to see what kind of the local stress will be. Local stress. And so this one is based on the stress concentration factor. Sigma local equals the sigma infinity multiplied by 2 square root of 2a1 divided by rho. Right? So this one, if we know sigma infinity, and then we can write sigma local. Local means that just near the crack tip, the bigger crack tip. And so we have this sigma local. And this sigma local and will be equal to this is so this is a penny shape, this is a crack, this is a bigger crack, this is a penny shape. This is for penny shaped, and we have this equation, sigma f penny equals this. And this equals this. So we just want the local stress equals this is sigma penny, the failure. And then we just let this equation, and based on this equation, and we can calculate A2. So A2 is so this is A2. Finally, this A2 equals this pi rho divided by 16 1 minus the nu square. And so here this is you can calculate the nu equals 0.3, and then you can calculate the A2 here. Questions, guys? Questions? So there are 2 steps. On the first step, and based on the stress concentration factor, we establish the relationship between the local stress and the infinity stress. Right? Is infinity stress. So this is the sigma f for the through thickness crack. Sigma f equals this. You can just put in, okay, I know, under this condition, when the sigma f equals this, the through thickness crack will will start grow. And I know this is sigma f, right? And put in this is sigma f, and put in sigma infinity here, then I have this sigma local. Why I need to calculate sigma local? And because this penny-shaped crack is in the neighborhood of this is a bigger crack tip. So this value, okay, so this value is a local stress. I want to see when this local stress can cause, this is a penny-shaped, the small crack grow. I just let these two guys equal each other, and then I can calculate the A2 here. You can see A2 is related to Poisson's ratio, and also, and so this rho is a curvature of the bigger through hole crack. You have sense, guys? Alexis, are you okay? Yo, because this one, and this one I know sigma f for the bigger crack is through thickness hole crack. I know sigma f equals this one. I want sigma f equals sigma infinity. So based on sigma f here, I know that the local, for the local, I get sigma local equals sigma infinity, which equals this sigma f, multiplied by the stress concentration factor. And then I want this sigma local equals the sigma f penny, because I want to see under what condition my penny shaped the crack grows, right? So I just equate, let this guy equals this. And then this one equation, you can I see we have one equation, and you can just get this is A2. I want you guys to derive this one a little bit. What? And then we talk about the energy release rate. So energy release rate is a very, very important concept in the fracture mechanics. So this is the Professor Irwin, 1956, and then many years ago, almost 70 years ago, right? Almost 70 years ago, Professor Irwin and proposed this equation. And so it says that this is a G energy release rate equals, pi is a potential energy, We take the derivative of the potential energy of the whole cracked body, and with respect to A, capital A. And keep in mind, capital A is a crack area. Capital A is a crack area, right? Crack area. This crack area is not a surface area. And crack area here is a projected crack area. So projected crack area means that this is just a crack. And length multiplied by the thickness. The surface area is double, because usually whenever we have a crack, or we have two surfaces. Crack area and surface area, and there is a factor of 2 there. Okay, so the G, the energy release rate, and G is a function of the geometry of cracked body. The definitely is related to the load and how much load you apply, and also the material parameter of this guy, Young's modulus and Poisson's ratio. And we only take care of these two guys because at this stage, we only considered linear elasticity. So that's a linear elastic. The material, we only have two independent variables. One is Young's modulus, and one is Poisson's ratio. So this is we have a function. This function needs to be determined. So this pi here, you can see, okay. And in last class, pi equals pi 0 minus pi sigma square a square b divided by Young's modulus. And sigma is the stress you apply, and a is the crack length, and b is the thickness of the plate. And so we have this equation already. And pi 0 is, what's the pi 0, guys?
Potential energy of a cracked body.
Yeah, David. Thank you very much. The pi 0 is the potential energy of the system before they have any crack. The potential energy of uncracked body with the same geometry and with the same loading condition, same material. Now, the dA, okay? And dA equals d and 2ab. This is the through thickness hole. This is a through thickness hole. And through thickness hole, let's see, this is through thickness hole. Is a through on thickness hole. Right, so this is the B. And through thickness hole, and this guy's crack length is denoted as 2A. And that's the reason, and the dA and the crack surface equals 2AB. 2A is the length of the crack, B is the thickness, and D 2AB. And because B is constant, so this dA equals 2B, D capital A equals 2 capital B multiplied by dA. Bobby.
Is this only for the through thickness crack right now? Like.
Yeah, these are through thickness. And for the edge crack, and here is for edge crack, and we have A here. For edge crack.
Oh, okay.
For edge crack, and we have these kind of things. So this is edge crack. So here is denoted as the A curve length. Now, this is the dA equals this one, okay? dA equals 2B and lowercase dA equals 2B dA. Right? And then we look at the G, and G is a derivative of potential energy with respect to dA, and so this one, and actually this G, and equals d pi and dA, right? And then we can get, because based on the calculus we have learned, and d pi dA, and we have d capital A, we have equals d pi d lowercase a multiplied by d lowercase a and d capital A. You guys agree with this step? This is called chain rule, right? This is called chain rule, and d pi dA, okay? For here, d pi and dA equals what? Equals dA pi sigma square, and here is the exponent equals 2. We just put 2 goes down, right? And then we have 2 pi sigma square A B. So this one gives us minus d pi dA, lowercase dA equals Young's modulus and 2 pi A square. I'm sorry, sigma square. 2 pi sigma square and A and B. So this is the d pi lowercase dA. And then I have dA dB. dA dB equals, and dA dB equals what? Just put equals 1 to B. Right? You guys agree? Okay, okay. And you just multiply by and 2B. And then we have this 2 cancels this B cancels this. As a result, and we will have minus pi sigma square A and divided by E. So this is and how we get here. E pi dA, I'm sorry guys. So here is the pi 0, is a pi 0 here. This is a pi 0 is constant minus. So this is minus, this is minus, so we have plus here. Questions so far? So because we have a minus here, so then we have another minus. Pi 0 is a constant. And the constant means that because this guy has nothing to do with the crack length. What? It has nothing to do with the crack length. And that's a result, that is as a result, and this guy is constant. Question so much? Okay,
Where does the DB come from, the capital DB? DA over D, capital B?
yeah, you are right, you are right, you are right. Good, thank you, thank you. Thank you. You are right, yeah, DA, yeah, capital A.
Oh, okay.
Capital A here, you just plug in, it's a 2B. Yeah, I'm sorry. Then we have the energy release rate equals this one. You can see this guy is related to the load you apply and also related to the current, the current length, and also Young's modulus. Now, based on this one, you can get the T, energy release rate. And usually we have the TC, and TC is a critical energy release rate based on the material. If this equation holds, that means the crack tends to grow. And that is very, very critical state, and you need to be very, very careful. So usually we want the T is much less than the TC. The GC equals dWs divided by dA is area. Ws is work to create a new surface. And we have another omega F. Omega F is a fracture energy, and it includes plastic, viscoelastic, or viscoplastic effects, depending on the materials. So this is omega F Ws. Omega S, you can call it omega S or Ws. We call Ws, work to create a new surface. And work, Ws, work, S is a surface. And how much energy you need to get the new crack. So give it a TC. So this is our first energy release rate equation. It is for the through thickness hole and 2A, and how to calculate this guy's energy release rate, and then we compare. So calculated energy release rate with the critical energy release rate TC, and then we see whether this crack grows or not. Questions? No question? No question. We look at I will introduce two important concepts. One is called load control, and this is second one is the displacement control. Have you guys ever heard these two concepts? Okay, you can see as the name suggests, load control. I have a sample. The load does not change. I want to see how this material behaves. It's load control. And the displacement control means that is the same. This is a specimen. I fix the displacement, but I do not change the load. Only the displacement is fixed, but the load is changing. So this is one called load control, one called the displacement control. You can see load control here. I'm talking about the cracked body, and you can see this edge cracked body. So here I have a weight here, and the weight P does not change. Weight P does not change. So this is what I want to do. I want to see on how the crack length affects this guy's displacement. P does not change. And what I want to see is the relationship between the crack and the displacement. You can see right here. So potential energy, we have this potential energy of elastic body. We know that potential energy of any elastic body equals the straight energy and straight energy U stored in the body, and the minus F here does not stand for the force. It stands for the work done by the external force. The work done by the external force. If we know the string energy and also the work done by the external force, and we will know the potential energy of the whole system. So this is the equation. U pi equals U minus F. And first we talk about the load control. Load control, this is a system. Because in the load control, we know that the force applied, this is by applied to this system does not change. And if we know this guy's the P and also the delta, the deflection of the delta, and we will know the work done by this P. Do you guys agree? The force remains constant. The force multiplied by this displacement equals this guy's work. Right, guys? Force multiplied by the displacement in the force direction equals the work this guy has done. Right? So F equals P multiplied by delta D. And just let's look at this is U. And U is the string energy. And how the string energy is changing. And we know that this is a P, okay? If you apply the P, so this guy, what will happen to this guy? This guy will strengthen, right? Will have some deflection. So this deflection is a P multiplied by delta C, D delta, where D delta, how far it goes. If not P multiplied by D delta equals the string energy. It's a force, it's a work. And then you just do the integration from very beginning unto this current delta. So this one will be the string energy. Got that? One more time. So when you stretch something, the string energy equals the load you apply multiplied by the deflection you have, and within that infinitesimal, this is the delta. All right? And then you can just do the integration. Then we get from very beginning and to the applied delta, and using this equation, and you will get the string energy. The string energy is dependent upon the material. If you pull something, and you will cause the string energy in the system. Definitely, you are doing work also. Bobby?
So the work is twice the strain energy?
You are right. For this case, it is. So look at it here, okay? So look at this graphic. The graphic, as I said, for this one, my load is the constant. And what I want to see is on how the displacement is dependent upon the load crack, the crack length. You can see here, displacement, so this is a load. You can see for here at this point, this line, okay? So this line is for the crack length A. For crack length A, I have this straight line. If I have a crack length A plus dA, that means just a little bit, very tiny increment dA, I have this one. Why? Because I know that if my crack increases, what will happen to my material, to the specimen? This can become softer, right? This can become softer means that same load, and I will have a bigger displacement, bigger deflection. So that's the reason. And so this will be my A. I can use this line to denote A plus dA. So you can see here, okay? So this is a shaded area equals the change of the string energy. So this one will be the this is the load multiplied by D delta and will be the force of this external load. So this, we know that, so this is rectangular shape, so this is a triangle, is the area of this triangle equals and half of this rectangular shape. You guys agree? Both. Okay, so look at here. That is for from the graphic perspective. And for if we use equation, this is our F, and this is the U, and then we potential energy equals this guy minus the U minus F, and we know that this equals one half PW, which equals minus U, which minus U. So G equals d pi dA. So this equation we have learned this one, right? Yes. D pi dA, you can see, and this is of A equals, and so A, capital A equals, lowercase a multiplied by B. Where is the factor 2? Because here is this is the edge crack. You understand that? Some students might ask, Doma, so in the previous equations you said, and the capital A equals 2 lowercase a multiplied by B. And for here, where is the factor 2? And for this one, we are talking about this is a through hole, the crack, through hole, through thickness hole, crack, through hole. But for here, for simplicity, we focus on this edge crack. Edge crack length is denoted as A. And through thickness hole, the crack length is denoted as 2A. That's the reason the factor 2 disappears. You can see the factor 2 disappears. The dA equals thickness of this plate multiplied by the A, lowercase a. So we can have this equation, and then is a U, right? Is a U, and we just get this is a delta. Keeping in mind, and we are getting the relationship between this is a deflection and the crack length. That is what we are looking for. That is what we are looking for. Understand, guys? Any questions regarding this? Bobby?
Is that P, the subscript P?
Subscript P?
Like the du over dA?
Yeah. Okay, good question. So this subscript P means the load control. Load control. I'm sorry. I did not mention. And for later, when we talk about the displacement control, we use another letter. We use D. Thank you, Bobby. I want you guys to be attentive and to be aggressive. Whenever you have a question, ask. And then after this class finishes, you don't need to do anything extra. And only before you go to bed this evening, then look at the lecture notes to refresh your memory. And then you will definitely get an A, right? I'm not hoaxing you. That's true. That is a very, very effective learning strategy. Questions? So one more time. So this subscript P means that, and here we are talking about load control. So graphically, we can see graphically what I just talked about, and graphically, and du is du equals OED minus OBD. So this is OED minus OBD, and finally we find out this equals 1/2 P multiplied by delta D. The dF, so dF equals, this is the D delta multiplied by P. This is the shaded area. So this is I'm sorry, this is with the zebra line. So this is this area. So one more time, I want to let you guys know, load control and the displacement control. We want to establish the relationship between crack length and deflection. What? If the crack length goes, if the crack length increases, and what happens to specimen? So you can look at the G, and here is the G. Same thing here. What? So this is G equals du minus df, u minus f, u minus f equals pi. And du df, du da, and just plug in graphically, and you will have the same equation as this one. So this P means load control. Questions, guys? No question? We look at the another one, opposite one, the displacement control. Displacement control, you can see as the name suggests, the displacement is fixed. The same specimen, I have the same displacement, but I'm going to increase the crack length a little bit, a little bit, a little bit. And then what I want to calculate is on how the crack length affects this is load here, right? You can see the delta is fixed. The testing machine is for here, delta is fixed. And theoretically, it means the testing machine is infinitely rigid. The displacement is fixed. That means you cannot move it at all. That means this testing machine is infinitely rigid. So because delta equals 0, because the displacement does not change, right? The deflection does not change, means that deflection is constant. And deflection is constant means what? Even if you have a load, this load does not create any work. Right? Because delta is constant, d delta equals 0. You guys agree? When d delta equals 0, and then no matter how much p you have, and p multiplied by d delta equals 0, and then this is df, this is f, and then if you do the integration over 0 is 0. If integrand equals 0, that's definitely 0. Right? That means for this is the displacement control, the external force does not create any work. And that means the potential energy of the whole body is only related to the street energy. Right? Okay, guys. So you can see pi equals street energy U. It equals 1/2 pi, 1/2 p multiplied by delta. 1/2 p multiplied by the delta. So where we get this, how can we get this one from here? U is always, no matter what happens, U is always obtained using this equation. And p multiplied by delta U, and then we do the integration. And then we have, after we get here, guys, this is pi, and then we just take the derivative of d pi, and we respect to the capital A, and capital A here equals 2 lowercase ab. So we can have this one. Keep in mind, because there is a d here, for p and delta, delta is constant. Delta is constant. And for load control here, P delta and P is constant. That's the reason you can take P out. But this delta is still a function of A. Okay? You have sense? That is the difference between load control and the displacement control. So for displacement control, as I said, this delta is constant. That's the reason I can take this out from this derivative sign. But the P is not constant. The P is related to the crack length. P is related to the crack length. And you can see here, so this is the graphical. So graphically, du here, du is a du, and du equals the change of P multiplied by the displacement. And the displacement does not change, but as this is the crack length changes, the dP changes. So this is still, this shaded area is du, the change of the stream energy, which also equals the change of the potential energy. Because under this condition, potential energy equals stream energy. You can see here. Graphically, du equals OCB, OCB minus OAB. OCB minus OAB, right? OCB minus OCB, this area, minus OAB. That means this is the potential and this is the shaded area. And it is, this is negative one, this is negative. And because we know that if the load, if the displacement does not change, and if the crack becomes bigger, and then the P will become smaller, right? That means if the crack grows, and so this specimen becomes softer in order to have the same amount of displacement, and you just need a little bit smaller the force. So that's the reason, and so we can see the force is changing from A, original crack length, and to this new crack length, A plus dA. So that's the reason we have this negative sign here. And so we can see the G equals d pi dA and du and dA, and here this is dA here, okay? And we have this delta and A, and this is a 2 dP and dA, and we have, and also can get the same equation on both mathematically and also the graphically. So this is the G here. So as a result, energy released for these two case scenarios is obtained. And for this D control, D is a displacement control. So G equals using this equation, and in which the P is a function of crack length. P is a function of crack length here. For load control, and on the contrary, and T equals this one, you can see for this case, P is a constant, but the delta, the deflection is dependent upon your crack length. You have sense? Are you guys okay? Okay, compliance. We just have this as a concept, compliance. And compliance means the displacement divided by the required load. And this is compliance. And we have a stiffness, right? So this compliance equals the displacement divided by the required load in order to achieve this displacement. So if we have this using this equation, we can just write P in this equation, P squared 2B divided by dCdA. So this equation is working for both load control and D control. Questions? Move on.
So the stiffness changes? Does
Yeah,
the
stiffness is the reciprocal of C.
in both cases, the stiffness?
Yeah. Yes. What? Yes, but you keep in mind, in which condition, what is constant and what is changing. For loading, for this displacement control means the displacement remains the same. The changing variable is a P. It's a load required to achieve the same amount of displacement. For load condition,